Hello, this is Team Shifters from the Embedded Security and Hardware Hacking class, consisting of me, Aiden, Zawad, Alex, and Tom.
Embedded systems, first off, we learned about the classification and what identifies an embedded system. So these are usually just small, specific purpose devices. And we learned about like the specific hardware requirements that creates an embedded system. So something like the ARM chips that are usually found in mostly embedded systems. Uh, we got familiar about how to use documentation to program embedded systems because a lot of times they give you a wealth of information and we have to figure out how to process that information and be able to use it. We learned about communications programming, so serial and UART, and between different programming languages, so Python and C. We learned about bitwise operations, so that's working with binary and left and right shifts, XOR, and logical operators. And we also learned about just direct programming to hardware, such as just firmwares and how a bootloader is created and built.
For the security part of embedded security, we learned about cryptographic algorithms and more specifically encryption algorithms like AES and RSA. We also learned about authentication and hashing, examples of which would be SHA and HMAC. We then learned how to take advantage of implementation errors, which are very common in such systems. And some of those implementation errors make us able to allow us to do a side channel analysis, and a very famous implementation error allows for the Spectre and Meltdown vulnerabilities. And finally, we began working on the challenge.
Now, even the best designed security protocols can be worked around. Like, you might want to build a fence for that road. The security checkpoint can just be bypassed.
All right, so moving on to the design challenge part of this. Here's a flow diagram representing our design for the final challenge. So the challenge was to imagine a scenario in which you're a company trying to update the firmware in your remote self-driving car, and you need to securely write that firmware to the car without it being corrupted on the way so that the car doesn't get hacked, essentially. So what we did was we used the RSA asymmetric encryption algorithm in order to sign and authenticate the data that's being transmitted to the bootloader. And we used the secure hashing algorithm 256 to hash the data that's going to be authenticated. And then finally, we used the advanced encryption standard, or AES 128-bit key size, in order to encrypt the firmware that would be sent over. And to the right, you can see a full flow diagram of our security protocol that includes all the specifics on exactly what we're adding to be sent to the bootloader.
So we considered what type of threats we could be facing when designing our system, and we realized, well, most of us are high school students, and I don't know anyone that has a quantum computer. I personally don't, so we thought, okay, that's probably something we can consider to be safe. We're virtual this year, and so we didn't have to worry that much about hardware level attacks. We did consider that we could be vulnerable to a replay attack, a buffer overflow attack, and a side channel analysis attack. We specifically did design against buffer overflows and replay attacks.
So our implementation uses RSA, which is asymmetric encryption, and it turns out that we were actually the first team in the entire history of this program to successfully implement the asynchronous cryptography. So
we also checked the size of the encrypted firmware against the maximum size required, and if it was a multiple of 16, we didn't accept any more bytes to prevent a buffer overflow attack that similar to one that we would have used on other teams. So this is a very important part of embedded security, making sure that you can't just bypass everything.
However, despite all of this preparation work, there are a few things that if we would do this project over again, we would change next time. The first thing would have been to try to become familiar with more advanced C topics earlier on in the course. This would have helped greatly with debugging and just writing the project in general. as well as using some of the cryptography tools that we were assigned to. Next, getting familiar with the APIs that we used. Namely, there's one library that contains a lot of crypto tools called Bear SSL, and it was very challenging to implement, and being familiar with this earlier would have helped greatly in speeding up our design process. And finally, if we were to not be virtual next time, we would have implemented measures into preventing hardware level attacks that could be implemented against us if the embedded device that we were working on had not been emulated, if it had actually been physical and real.
So to approach the attack phase, we first analyzed other teams' code and just saw like obvious things that could be exploited. So we also looked for things that we know we protected against, and we considered when we were developing our code, and we tried to see if any other teams forgot about a certain type of attack. And most of these attacks we were taught about and we were told to consider when designing. For example, if we realize if the buffer can be overfilled, there's a very good chance that we could maybe bypass the authentication and skip the encryption altogether. And some tool we found useful in finding these exploits was GDB, and here is an example of that.
So we tried a couple approaches in the attack phase, and we settled on a pretty simple one that we saw. There was a major there was a major issue with one of the team's codes, which meant that we could overflow the buffer. So we used GDB to find the memory addresses of certain functions, specifically the boot function, and using the buffer overflow attack, that allowed us to directly skip from really an authentication failure directly to booting the firmware, which was is a pretty interesting attack. And other things we could do with overflow attacks that we've considered are just overwriting keys or directly like erasing certain parts of memory. So there we go.
Yeah, we did it.
Diagnostics. We just got the keys.